Hey kids, Creepy Baby here. In this exciting episode of the podcast, we're going to look at topics involving the impulse momentum theorem. Now, the impulse momentum theorem states basically what it takes to change an object's momentum. In order to change an object's momentum, an impulse must be delivered. Well, what's an impulse? It's when you apply a force over a certain period of time, resulting in a change in momentum. You can write it out as an equation by saying F delta T equals delta P. This equation relates how the force, when applied over a period of time, will change an object's momentum. But the impulse itself, the physical quantity impulse, relates to either one of these sides of the equation. Both of these relate to the impulse delivered. So if we have a question here, like a person kicking a soccer ball with a force of 1,400 newtons, and their foot touches the ball for 7.9 times 10 to the minus 3 seconds. Doesn't take long to make that soccer ball go. Well, with that force and that time, what impulse is delivered? Well, given information, you wouldn't work on the left-hand side of the equation. Again, either side of the equation is the impulse. The entire equation relates the impulse to the change in momentum. So working on the left-hand side of the equation, we substitute the 1,400 for force 7.9 times 10 to the minus 3, and that gives us an impulse of 11.06, or if we go to two sig figs, 11 Newton seconds equals the impulse. The units involving impulse and momentum, they're nothing special. You just take the units in the equation, slam them all together, and you've got units of impulse and momentum. So a kilogram meter per second of momentum is equivalent to a Newton second of impulse. Well, look at part B of this question. If we deliver this impulse to the soccer ball, with what speed will it take off? We're assuming, of course, that you're kicking the soccer ball from rest. So again, delta P is going to be final minus initial. But since the initial is 0, just the final momentum is the change in momentum. So we can say here that 11 is mass times, and we'll put the delta in here, VF minus VI. You see the mass MVF minus MVI, and the mass factors out. We can just cross this out because initial velocity is 0. So 11 equals, and I looked up on Google, the mass of a standard soccer ball is about 430 grams. So that would be 0.43 kilograms times the velocity that it takes off with. And solving for final velocity, we get a final velocity equivalent to 26 meters per second. So while the impulse is 11 Newton seconds, you can take the question a little bit further and go into the change in momentum to actually find what the final velocity is. So there's a couple different ways you can look at impulse questions. You can find the impulse, or you can use the impulse to see how the momentum changes. Another common kind of impulse question is when you throw a ball against the wall. The wall applies a normal force to the ball, and the normal force delivers an impulse to change the ball's momentum. In this situation, we've got a ball incoming at 12 meters per second. It bounces off the wall 10 meters per second. Now again, it may look like we're losing kinetic energy here, but keep in mind that the ball deforms, and that's going to change the thermal energy of the ball. You hear it hit the wall, there's going to be some vibration carried through the wall. So all these are ways that energy leaves the ball when it strikes a wall. And so we actually would expect it to rebound at a slower velocity than it hit the wall with. You notice that due to the vectors here, the vectors make it obvious that there's a change in direction, which means we need to make sure we establish a positive direction. Let's let incoming be the positive direction. So I'll draw another vector here and circle it to show that incoming is the positive direction. And so we'll write the impulse momentum theorem down. We'll say that F delta t equals the change in momentum. Now if we want the impulse, this time we don't have force and time data, but we've got enough data to find the change in momentum. So this time, to find the impulse, we'd want to work on the right-hand side of the equation. And we'll just stay exclusively on the right-hand side of the equation because there's no information, there's no question about what force or how long is the ball in contact with the wall. So if we just want the impulse, all we need is the change in momentum because the impulse is equivalent to the change in momentum. So we'll expand this to say P final minus P initial. And again, this minus sign comes from just the definition of the delta P, final minus initial. The final momentum is 0.057 times, now since we said incoming was positive, this 10 is actually a negative 10. This minus sign comes from the delta, and then I'm just going to put m because I'm running out of room on the paper here, m times positive 12. We'll see the mass factor out of here again. And so we'll have 0.057, because the mass appears in both terms and factors out. We have negative 10 minus 12. So that's 0.057 times negative 22. And that gives us an answer of negative 1.3. And I'll stick with the units of momentum since we started with momentum, kilogram meters per second. And the impulse is represented with the letter J. Go figure that out. But hey, I'm telling you here in the video. So the impulse is negative 1.3 kilogram meters per second. Now again, this is a directional negative because we said incoming is positive, so the normal force directs an impulse going back the opposite direction, which is what you'd expect. The wall, the wall provides a force opposite to the way the ball came in. So this all depends on your frame of reference, but following the frame of reference we chose. Now notice, because of this positive negative business, you always, when you've got a ball bouncing off a wall, you're going to, instead of subtracting the delta, you're going to wind up adding the two absolute values of the incoming and outgoing velocities. That might be a little shortcut to keep in mind, but you'll always wind up adding these two numbers, and then your final answer is going to be positive or negative based on whether incoming or outgoing was positive in your frame of reference. So with the impulse momentum theorem, we say that a force applied over a period of time is the impulse, or it causes a change in momentum, and either side of this equation is the impulse itself.